Okay. Now let's go to the next problem. The next problem is about Laplace equation. So this is Laplace equation. Uxx plus uyy is 0. In the plane region, that is, we have a x, y, x coordinate system. X lies in 0 and 1. So for x 0 to 1, 0, 1. Y from 0 to 5. So this is the region, a rectangle region. Okay, so the function is defined in this region. So we have the region where the equation, the unknown function is defined, the domain of the unknown function. Okay, and the geometrical condition on the edge. So this is a rectangle. We have 4 edges. So at the edge y equal to 0, y equal to 0 is this part. This part y equal to 0. And y equal to 5, that is the upper boundary, the top of this rectangle, and the bottom of this rectangle. We are imposing the zero-Dirichlet boundary condition, meaning that u is 0 here. Okay? And for the x equal to 0, when x equal to 0, that is the left boundary. Left boundary. What color should I use? Oh no. On the left boundary, u equal y square. And on the right boundary, when x equal to 1, u equal 2 sine pi y. That is the problem. So as before, we need to formulate the problem mathematically and then solve the problem. Okay? So the formulation, mathematical formulation, first goes the equation. Okay? Then the boundary condition at the bottom of the boundary of the region. Okay? That is when y equal to 0. So we know that in this case u is 0. And also the top boundary. So when y equal to 5, u is also 0. Okay, these are the zero-Dirichlet conditions on two edges of the boundary. And for the left boundary, left part of the boundary, we also impose the Dirichlet condition, but not zero-Dirichlet condition. The boundary condition is given by a function y square. Similarly, on the right part of the boundary, when x equal to 1, we are given u equals to 2 sine pi y. So this is the problem. This is the initial boundary problem corresponding to what has been described in the statement of the problem. Okay, so this is the answer to question 1 for the problem. Next, we need to find the product solution and formulate the eigenvalue problem. So because now we are not xt, we are xy. So we write u as a multiple of a function of x and a function of y. That is u equals capital X, capital Y. Then as before, you need to compute the corresponding derivatives appear for this u appears in the equation. Now we have uxx and uyy. First, uyy is xy double prime, and the uxx is x double prime y. Then substituting this uxx and uyy into the equation, we have what? We have minus uxx equals uyy. This is equivalent to uxx plus uyy equals to 0. Now minus uxx is minus x double prime y, while uyy is x y double prime. So dividing both sides of this equality by xy, we get this equality, where the left-hand side is a function of x, while the right-hand side is a function of y. So this has to be a constant. That is, for some lambda, this equals to minus lambda. Therefore, the capital X satisfies this equation, this ODE. So we obtained this ODE for capital X. And this is the ODE for capital Y. Both of these two ODE follows from this equality, right? Okay. Now we need to consider the boundary condition. So our boundary condition, here we have a problem. What boundary condition should be used to make the eigenvalue problem? That is the problem. What boundary condition should be used to make the eigenvalue problem? You should have an eigenvalue problem of this form: x double prime minus lambda x equal to 0, x at 0 and x at 1, or you should have y. This is a problem. For y, you should have y double prime plus lambda y equal to 0. Maybe y0 equals something. Y1 equals something. Okay? We need to make a decision. How to make this decision? Well, you need to take the 0. So our u has our u is 0 on the top and the bottom boundary, and u is not 0. It's a given function on the right and the left boundary. So you need to take the left, the top and the bottom, because at the left and the bottom boundary, u is 0. So you need to consider this this boundary, u x 0 is 0, also ux phi. Okay, you need to use this. That means x y0 is 0 equals x y phi. So you have y0 equals to 0, y phi equals to phi. And then these two conditions are under the ODE for y, consisting our eigenvalue problem. So you should not work with x. If you work with x, your x or its derivative will not be 0 at the endpoints of the interval. So you do not have a correct eigenvalue problem. Okay? So this is what I need to mention. Therefore, using the boundary condition, when y equal to 0, so x0, xy0 is 0. Then this forces y0 to be 0, as I just mentioned. Similarly, at the endpoint y equal to phi, this also forces y phi to be 0. So y0 is 0, y phi is 0, equals to 0 under the ODE for y, consisting our eigenvalue problem. This time not for x, for y. Instead, it is a boundary problem for the factor y. Okay, so this is the eigenvalue problem. Okay, so this completes the second question. The third question, we need to solve this boundary problem. Solve this eigenvalue problem. As before, we need to distinguish three cases: lambda negative, lambda positive, and lambda equals to 0. So when lambda is negative, the general solution for the ODE for y is linear combination of this exponential function. Then our boundary condition tells us that y0 is 0. So y0, on the other hand, by the expression for y y0 is the sum of C1 and C2. Okay, and also when small y equals to phi, so y capital Y phi is also 0. But this is also linear combination of exponential of some quantity. Okay, so this two equality considered as a linear system of equations, and you can solve this to get C1 and C2 are all 0. Therefore, the corresponding y is identically 0, and this means that when lambda is negative, the eigenvalue problem can only have 0 solution, so lambda is not an eigenvalue. Next, we consider the case the lambda is 0. Now, the general solution is a linear function for small y. Okay, then using the boundary condition, y0 is b, therefore b is 0. But y phi is phi a, y phi is also 0, so a is also 0. So a and b are all 0, therefore the corresponding y here, is also a 0 function. So as before, this means that when lambda equals to 0, the only solution of the eigenvalue problem is the 0 function. So 0 is not an eigenvalue. Okay. Next, we consider the case that lambda is positive. So when lambda is positive, the general solution is linear combination of sine and cosine. Therefore, applying the boundary condition, so y0 is 0, but y0 is linear combination of sine 0 and cosine 0. So since sine 0 is 0, this is C1. Now y phi is also 0, but y phi is linear combination of cosine phi square root of lambda and sine. So, but we already know that C1 is 0, therefore we only have C2 sine phi square root of lambda. So we don't want C2 to be 0. Since C1 is already 0, if C2 is also 0, then the capital Y is 0. Okay, so we don't want the 0 solution. Therefore, sine phi square root of lambda has to be 0. That means if you want lambda to be an eigenvalue, phi square root of lambda has to be a multiple, integer multiple of pi. That means we have a sequence of eigenvalue lambda n, which equals n pi over phi square, n from 1 to n, 1, 2, 3, and so on. Okay, and then correspondingly the eigenfunction is yn. Why this is yn? Look at the expression for capital Y here. Okay, look at the expression for capital Y. Because C1 is 0, so the solution for the eigenvalue problem, that is our eigenfunction, is sine square root of lambda y. But the square root of lambda n is n pi over phi. So this is the reason that yn is sine n pi over phi multiplying y. Okay, so up to now we have solved the eigenvalue problem. We know that we have a sequence of eigenvalue lambda n, n from 1, 2, and so on, and we also find the eigenfunction. Okay, so this is the solution of the third question. Now the last solution of the initial boundary problem for our Laplace equation. Now up to now we only know capital Y, but we still don't know what capital X is. So to find the capital X using the lambda n, we can solve capital X from the equation 3 here. That is the ODE capital X is satisfied. Here the lambda is the same as that of y. Therefore the lambda should be lambda n. For every lambda equals to lambda n, we can solve this ODE for capital X. This gives us capital X is a linear combination of exponential function. Remember? Let's go back to the ODE for capital X. Capital X double prime minus lambda x is 0. Now our lambda is what? Lambda is n pi over phi square. So x double prime minus n pi over phi square x is 0. So from this you can find the general solution, okay, which is a linear combination of exponential function. Now, having obtained the capital X, that is our xn, we can construct the product solution. This product solution satisfies the boundary condition on the top and the bottom boundary of the domain. Our region is this rectangle. Our yn is 0 on top and on the bottom. So our un equals x and yn. Of course, it's also 0 on the bottom and the top of this rectangle. Okay, so this un, the multiple of xn and yn, satisfies the boundary condition on the top and the bottom boundary, and also satisfies the PDE, the Laplace equation. Therefore, this is a solution. But so this solution, x and yn, yn is sine n pi over phi y, and xn is given at the second line of this slides. Therefore, this is the expression for un. This un, as I said, satisfies the Laplace equation under the boundary condition at the bottom and the top boundary. But it might not satisfy the boundary condition at the left and the right boundary. Okay, our rectangle has 4 boundaries. Now, on 2 of the boundary, the boundary condition is fulfilled, but the left and the right still not fulfilled. We need to construct a series solution, that is this u, and choose the an, the coefficient an and bn suitably to see whether this u can satisfy our boundary condition at the left boundary, that is when x equal to 0, and the right boundary, that is x equal to 1. Now to do this, remember our ux0. What is our ux0? I need to go. Yes. Okay. When x is 0, u is y square. So our u is y square here. And when x equal to 1, u is 2 sine pi y here. Okay. So we have this expression for u, which is the unknown an, bn. An and bn are to be determined. Okay, how to determine the an and bn? We apply the boundary condition when x equal to 0. So the boundary condition says that u0y equals a square. But u0y is what? That is in the expression for u, the series expression, let x equal to 0. When x equal to 0, the 2 exponential functions are all equals 1. Therefore, simplified as an plus bn. So y squared is an plus bn sine phi n pi y. Similarly, when x equal to 1, u1y is 2 sine pi y. But to have u1y, again, using the series expression for u, set x equal to 1, we get u1y is this series. To continue our discussion, I copy these 2 lines to the next page. Here, okay? So these two equality, these two equality means that the coefficient an plus bn for the first equality and the an e to the phi n pi over phi plus bn e to the minus n pi over phi, these two sequence of numbers are the Fourier sine coefficient of y squared and the 2 sine pi y. Okay? Again, as before, y squared and the 2 sine pi y are two functions defined over 0, 1. Okay? Sorry, no, 0, 1 is for x, but we are working for y, therefore that is y. So y squared is this function. Okay? It defined on the interval 0, 5. So it can be expanded as a Fourier sine series. Now, the first equality here means that an plus bn consists of the coefficient of the Fourier sine series. Okay. So similarly, you consider the Fourier sine series of 2 sine pi y. So by the formula for computing the Fourier sine series, we know that an plus bn is 2 over 5, the integral from 0 to 5, the function to be expanded, that is y squared sine n pi over 5y dy. And of course, I omit the computation of this integral. Similarly, this part, this coefficient, this green quantity is the Fourier sine series, the coefficient of Fourier sine series of 2 sine pi y. Therefore, we have the last equality here. So, when you're evaluating the integrals on the right-hand side of this equality, okay? Suppose the first integral an plus bn equals what? Equals this integral. This integral, suppose it is alpha n. Of course, it depends on n, but you can evaluate it. You can compute the integral. Okay. Similarly, the second is an e to the n pi over 5 plus bn e to the minus n pi over 5 equals this integral. This integral is can be also computed explicitly, and of course the value depends on n. We denote it by beta n. Then from this two equality, you can solve an equal to something and bn equal to something. Okay, which the final an and bn, which the final an and bn computed here. Well, this function, this u, is the solution. This u in the middle of this page, is the solution of our boundary condition for the Laplace equation. Okay, so this finished the problem 3. Okay, so these 3 problems are the 3 problems in our practice test. But it is important to present you one more problem, very similar to problem 3. The difference is that in problem 3, we are imposing Dirichlet boundary condition, 0 Dirichlet boundary condition at the top bottom and at the top boundary and at the bottom boundary. I replace this by Newman condition. Okay. Let's go back to see. So, so this is the problem 3. You see the blue words. On the edge y equal to 0 and 5, we are imposing 0 Dirichlet condition. Okay, that is problem 3. Now I make a modification. My problem 4 is similar, the same equation, the same region, that is the rectangle, but instead of 0 Dirichlet condition, I impose the 0 Newman condition on the bottom edge, that is y equal to 0, and the top boundary, that is y equal to 5. And as for the left and the right boundary, that is x equal to 0 and x equal to 1, I impose the same Dirichlet condition as before. That is this problem is now still the rectangle 0, 1, x, y. Okay, my reason is this rectangle. So what happened to my u? U is imposed zero Newman condition. That means Newman condition is du partial derivative. Okay, but at the here n is the normal unit normal to the boundary. The domain is supposed to be denoted by d. So at the bottom, n is the direction of y. Okay, on the bottom and the top, the normal is parallel to the y-axis. Therefore, the partial derivative, the directional derivative in the normal direction is just partial derivative of y. On the top is partial derivative of y. That is 0. Okay. On the bottom, the normal is opposite direction of y. Therefore, it is minus partial derivative with respect to y. This is 0. Of course, this minus partial derivative equal to 0 is equivalent to partial derivative with respect to y is 0. So you should take this into account. The Newman boundary condition is about the normal derivative, directional derivative in the normal direction. But in our case, because the top and the bottom boundary are parallel to the x-axis, therefore the normal direction is parallel to the y direction. So the normal directional derivative, is just the derivative with respect to y. In conclusion, this Newman condition means that the partial derivative of u at the bottom and at the top is 0. Okay, that is the problem. So, with this remark, the mathematical formulation for this problem first goes to the equation as before. Then, this is the Newman condition at the bottom boundary. Okay, I just explained the normal the directional derivative. The normal derivative is just the derivative with respect to y. Okay. Similarly, at the top, that is when y equal to 5. These two are all 0. Then the boundary condition at the when x equal to 0 and then x equal to 1 are the same as before. So this is the mathematical formulation for this problem. The difference of this problem and the previous one is only that I replace the Dirichlet boundary condition at the top and at the bottom by Newman condition. This result in the second line of this mathematical formulation. That is, we are not impose we are not required ux0 to be 0, but require the derivative of u with respect to y equal to 0. Okay. Now, this is the formulation. Now, the second question in this problem is to find the product solution and the eigenvalue problem. As before, we write the u in form of a function of x times a function of y. Then, computing the partial derivative appears in the equation. For this u, we see that uyy is xy double prime and uxx is x double prime y, and the equation becomes minus x double prime y equals xy double prime, and then dividing both sides by xy, we get minus x double prime over x equals y double prime over y. Then the left hand side is a function of x, while the right hand side is a function of y, so there has to be a constant, say minus lambda. Now from this, we see that x satisfies this ODE. X double prime minus lambda x is 0. And the y satisfies this ODE. Now applying the boundary condition. The boundary condition, because we are imposing boundary condition by the derivative of u with respect to y. So we need to compute uy. Uy is xy prime. So using the boundary condition on the top, on the bottom, that is when y equal to 0. So this uy is 0, but this uy is xy y prime 0. So y prime 0 has to be 0. Similarly, when y equal to 5, uy is also 0, but this is equal to xy prime 5. So y prime 5 is also 0. So the eigenvalue problem is y double prime plus lambda y equals 0. This is the ODE for y, and the boundary condition for y is y prime 0 equals y prime 5 equals to 0. Okay, so let me write this here. Y double prime plus lambda y is 0. Y prime 0 equal y prime 5 equals 0. Okay, so this is the eigenvalue problem. The next question is solving this eigenvalue problem. As before, we need to distinguish several cases: lambda negative, lambda equals to 0, and lambda positive. Now, when lambda is negative, the general solution is linear combination of exponential functions. But because our boundary condition involving y prime, so we need to compute y prime. Y prime is also linear combination of exponential functions. It is easy to compute. Then applying the boundary condition, y prime 0 is 0. So substituting y by 0 in the expression of y prime, we get y prime 0 is this. Okay. Similarly, for y equals to 5, we also have this. We also have this equality. So from these two equality, we see that C1 and C2 are all 0. This means that capital Y is 0. Okay? Therefore, when lambda is negative, the eigenvalue problem only has 0 solution, which means that lambda is not an eigenvalue. Okay? Next, we consider the case that lambda is 0. When lambda is 0, the general solution of this ODE, actually this ODE is just y double prime equals 0. So the general solution is a linear function. Y equals ay plus b. Then y prime is a. So using the boundary condition, we see that a is 0 and b is free. So from this we know that when lambda is 0, the eigenvalue problem has no zero solution. Any no zero constant is a no zero solution of the eigenvalue problem. So 0 is an eigenvalue denoted by lambda 0, and the corresponding lambda eigenfunction, we can take the constant function 1. Okay. Next, we consider the case that lambda is positive. When lambda is positive, the general solution of the ODE for y is linear combination of a sine and a cosine. And we also need to compute the derivative of y, that is y prime. It is also linear combination of sine and cosine, given here. Now applying the boundary condition, when small y equals to 0, substituting the small y in the expression of y prime by 0, we see that this equals this. But sine 0 is 0, we only have C2, square root of lambda, cosine 0, that is 1. Okay, we have this equality. Then we consider small y equal to 5. So y prime 5 is 0. But y prime 5 is given by this equality. So from these two equality, first we see that, since C2 is 0, y prime 5 is simply minus C1 square root of lambda sine. Okay. Now, so C2 is 0, and this is 0, but we don't want C1 to be 0 as before. If C1 is 0, then the capital Y is identically 0, so such lambda is not an eigenvalue. So C1 is not 0. When C1 is not 0, sine 5 square root of lambda has to be 0. This has to be true. okay? Because you don't want to say 1 to be 0. So from this we can see that we have a sequence of eigenvalue. Lambda should equals n pi over 5 square. For every n, you have an eigenvalue lambda, denoted by lambda n. N is from 1, 2, and so on. And then the corresponding eigenfunction is cosine. Why it is cosine? We have already discussed this several times. You see, capital Y is cosine, linear combination of cosine and sine. But the coefficient of sine is C2. C2 is 0. So the eigenfunction, capital Y, is only one term, cosine. Okay? So we have solved the eigenvalue problem. The last step is to solve the boundary problem. So as before, we already know we are talking about product solution u equal x, y. We already know y. We already have y. That is the eigenfunction, but we don't know x yet. So we need to find x. So for the lambda equals the eigenvalue, x satisfies the ODE 4. The equation 4 is the ODE for capital X. With the lambda, we can solve this ODE for x. This gives us the x. Then, when maybe I should copy the ODE to the board. X double prime minus lambda x is 0. Lambda n is n pi over 5 square. N from 1, 2, and so on. But remember, lambda 0, when n is 0, lambda 0 is just 0. So 0 is also an eigenvalue. So we need to consider n equal to 0 as well. When n equal to 0, lambda is 0. So x double prime is 0. So x is a linear function, ax plus b, denoted this by x0. And then when n is greater than 0, then xn, the solution of this ODE, for capital X is linear combination of exponential functions. The coefficients of the combination denoted by an, bn. So using this xn and our yn obtained before, we can obtain the product solution satisfying the boundary condition. Sorry, I have a misprint here. This this product solution, the condition that our product solution satisfies is not this one. It's uy when y equal to 0 equals uy when y equal to 5 equals 0. This is a misprint. So the product solution of the Laplace equation satisfying this condition at the Newman bound condition at the bottom and the top of the rectangle is given here. So u0 is just ax plus b. It's just x0 because y0 is 1. And the un is x and yn. And the xn is given here, linear combination of exponential, and the yn is cosine. Therefore, this is un. So we should find suitable capital A and Bn and the small ab, so that the sum of all these un, including u0, give us the solution of our problem. Okay, so the sum by our expression for u0 and the un, we see that u is given here. Okay, ax plus b plus a series consisting of an exponential plus bn exponential, then multiplying cosine. Okay, so to continue our discussion, I should copy the expression for u to the next page, to the beginning of the next page here. So this u satisfies the Laplace equation and also the boundary condition, Newman boundary condition at the top and the bottom boundary. But it might not satisfy the boundary condition, that is dirichlet boundary condition, at the left and the right boundary. So we need to choose suitable AB and the capital AN, capital BN, so that it also satisfies the left and the right boundary condition. Okay, that is when x equal to 0 and x equal to 1. So when x equal to 0, u is y square. U0 y is y square. But following the substituting the x by 0 in the expression for u, which has been copied at the top of this page, you see that u0y is b plus the sum of an plus bn cosine. Okay, you have this. Similarly, when x equal to 1, u is 2 sine pi y. So as before, you need to let x equal to 1 in the expression for u. You see that when x equal to 1, u is a plus b plus cosine series whose coefficients is an exponential plus bn exponential. This is just let x equal to 1, put x equal to 1 here. Okay, you set x equal to 1, you obtain here. Okay, so we see that the coefficient here, the coefficient for the expansion of u square, because this can be considered as the Fourier cosine series for y square. So y square is a function defined on 0y, 0,5, that is y square. Okay, so this function, of course, you can expand this function in terms of cosine. So this means that the small b and the sum of capital AN and capital BN are the Fourier cosine coefficient, the coefficient of the Fourier cosine series for y square. Similarly, a plus b and yes, this. Okay, a plus b and an, these are the Fourier cosine coefficient of 2 sine pi y. So by the formula to compute Fourier cosine, by the formula to compute Fourier cosine series, we know that an plus bn equals maybe I make some mistake. There is something wrong here. What should we have? Our b, you see y square is half of a square plus sigma n from 1 an cosine phi n pi y. So a square is 5 over 2, 0 to 5 y square dy. And small an is 5 over 2, 0, 5 y square cosine phi n pi y dy. So by comparison, you see that our b should be half of a0. Okay, and our an plus bn should be yes. My mistake is that here I forgot to write the a. I forgot to write the b here. The b is missing. I need to have the b. And for an plus bn, here is not sign. In the slides, the green sign should be cosine. So an plus bn should be 0 to 5 y square cosine phi n pi y dy. Okay, and for the coefficient here, for the coefficient for 2 sine pi y, that is from this for this expansion, for this part, there is also a misprint. For this part, what should we have? We should have a plus b. Sorry, maybe 2 sine pi y is half of A0 as before plus sigma an cosine n pi y dy. Yes, no dy here. Just n pi y. Oh, n from 1 to infinity. And the A0 is 5 over 2, 0 to 5, 2 sine pi y dy. And the an is 2 over 5, 0 to 5, 2 sine pi y cosine 5 n pi y dy. Okay? So comparing the Fourier expansion, Fourier cosine expansion of 2 sine pi y, you will see that a plus b is half of A0, where A0 you can compute. Okay, A0 is given by this integral, which can be computed. Okay, well, the complicated an e to the n pi phi plus bn e to the minus n pi phi is just equals to the Fourier cosine coefficient of the function, that is an. Okay, so we already determined the b here. Then we can determine the a using this. As for the capital AN and the capital BN, so this is an equality involving AN and BN. Combine this equality and the previous equality, that is this equality, we have a system of linear equation for AN and BN. AN plus BN equal to something, and the exponential of n pi phi AN plus exponential of minus n pi phi bn equals something. This something can be computed by evaluating the integrals. Okay, therefore you solving this system of linear equation using linear algebra. Using linear algebra, you can solve these systems of linear equation to get the value of capital AN and capital BN. Then with this value of capital AN and capital BN, our this U, we have determined the small a, small b, and the capital AN and capital BN. Then this U at the top of this page is the solution of our boundary problem. Okay, this strictly speaking, this problem could not be called a initial boundary problem, because this is only a boundary condition. There is no variable t, no time here, so it makes no sense to call the initial condition or initial problem. It is just a boundary problem. Okay, so this ends our lecture about the practice test. Okay.